Hi everyone. The title of my talk is a literature survey and critical evaluation of the latest ML-based IDS systems for IoT environments. I'll just give you a quick introduction about myself. So I'm a graduate student at the University of Southern California in Los Angeles. My areas of interest lie at the intersection of distributed systems, security, and machine learning. I've also been working with Intel in their part of the Kubernetes security team as well. So we'll just quickly go over what would be the table of contents and what is the summary of our talk. So we'll just start by understanding like what an IDS is and why do we need like separate IDS for IoT environments. Then we'll look at some of the taxonomy classifications what this paper has presented and some interesting observations from them. Then comes the main part of our paper where we discuss the pitfalls of using machine learning and how what are the limitations, what are the challenges we have using machine learning in this environment, and what should be the future scope of research and which directions should new research in the IDS space involving ML should be headed to, and some of our recommendations. The IoT environment, especially in recent times, has seen like a massive growth, both in terms of data volumes, threats, as well as usage in recent years. So it's very important for us to preserve the confidentiality and privacy of data, especially as there are more and more fields like transportation, industrials, and very critical domains like even self-driving, which use IoT devices. So protecting these network perimeters as well as hosts play a very important role to safeguard the cybersecurity space here. This paper actually discusses a comprehensive summary of the learning-based approaches. So there are like many approaches which have been done by researchers like supervised learning, semi-supervised, GANs, autoencoders, deep learning. So this provides a summary of all of those approaches and what does each approach specifically highlight, what kind of attacks does it tackle, and then what is the training methodology involved in each of these papers. So all of that is looked at in great detail. And then we look at the critical review of these. Then we use Daniel App's paper of the do's and don'ts in machine learning. So we take some excerpts from there and try to see fit into this space and see in our ML evaluating pipeline, we have like 4 different stages and what kind of biases, what kind of potential pitfalls we will be able to see in each of these phases. So what is an intrusion detection system? So as you all might be aware of, they are used to detect like Trojans, malware, spyware, and malicious traffic, which are inundating the system and the network perimeters. So primarily there are 2 kinds of intrusion detection systems, network-based and host-based. But in traditional real life, most of them are a hybrid combination. So we use both network-based as well as host-based. And also we use the distributed IDS because we want to leverage scalability and fault tolerance as well. So the importance of IDS for IoT environments. So we need like real-time response rate. And also IoT ecosystems generally have a heterogeneous tech stack. So they have different protocol layers compared to standard web systems. So that means that we need to design an IDS more tailor-made, or we need to make it more customized. And also an IDS which is designed for IoT environments has to operate under stringent conditions, for example, like low processing, because the hardware, there would be hardware limitations there, and it also needs fast response time. And the data, the protocols and the stacks might be very different. So the generic approach to security, what researchers have followed is to have the system not just engulfed in like traditional security mechanisms like authentication, encryption, firewalls, VPNs, etc., but also use machine learning in conjunction with these to protect the network perimeters. So some of the challenges what people face while designing IDS and IoT systems is hardware corruption, or like the physical layer itself is prone to DDoS attacks, gateway attacks, as well as packet sniffing. So IoT currently it's valued at more than like 400 billion today, the total market cap of all the devices. And then there are around 13.5 billion devices which are a part of the global ecosystem. So all of this makes even more important for us to prevent attacks on this network traffic. Especially with the recent development in deep learning and machine learning, more and more researchers are trying to leverage latest deep learning techniques, GANs, and other tools to prevent malware attacks. So we can just take a look at the brief overview of an IDS system. So generally, network intrusion detection systems are placed between the firewall and the router, and then host-based are on the host themselves. So host-based systems mostly use signature and pattern detection for detecting malware, whereas in IDS systems, they use like a four-step machine learning workflow. So we have to clean and train the data, then we build a model on top of that, and then that is used for predicting in real time. So so directly capturing data in real time and processing it in real time would be a tremendous computationally intensive process. So the models are basically trained on captured data beforehand, both benign and malicious, so that they can identify the threats in real time. So this happens before in a lab or in a testbed environment where the model is trained, and then that's deployed so that it can detect threats in real time. So ML and deep learning have proven really good in areas like spam detection, credit card for fraud, anomaly detection, etc. So that's the reason a lot of security focus in this field has been in using ML and DL for this. So in this paper, we have looked at various kind of classifications, first of all, like supervised, unsupervised, semi-supervised, deep learning, mix and match approaches, and also like there are new advanced tools which are being used today, like fog computing and edge computing in combination with these. So why do we need like a separate IDS for IoT ecosystems? So we already have a well-working IDS for traditional ecosystems, client-server architecture, as well as web systems. So why do we need it separately for IoTs? Because IoT requires special network and hardware constraints. So we have to work at a low level uh, uh, on a low level hardware, and it's not as powerful as your traditional hardware. So the model has to be lightweight but effective. Then also there's a lot of privacy rules in capturing IoT data. So we cannot capture all kinds of IoT data due to privacy and regulation laws in different countries and regions. So collection of data and a modeling of those features would be very different from a traditional ecosystem. Also, they face distinct security challenges uh, like hardware corruption primarily. So some of the taxonomy we looked at here uh, is super. So we have analyzed all of these papers in this paper. So we have looked at various supervised methods, unsupervised methods, semi-supervised methods, deep learning, and mix and match. So we found various interesting observations. For example, like semi-supervised with a combination of fuzzy clustering works really well. For example, the paper by Rathore and Park proposed a semi-supervised fuzzy C-means approach using both supervised and unsupervised for labeled and unlabeled outputs. We also found that, for example, supervised machine learning, especially the paper by Kherseth ETL and Hodo, so they have a really good accuracy and they do really a good job with a lot of DOS kind of attacks, but they don't do a great job, for example, with zero-day attacks. For example, unsupervised ML generally has a lower accuracy with respect to other kind of attacks, but has a very good detection capability on unknown or like zero-day kind of attacks. So different approaches have different advantages and disadvantages. So that's why the mix and match approach works best. So a lot of mix and match approaches use combination of supervised and unsupervised and a majority voting mechanism, or they use either a ML-based approach with an edge computing or a fog computing based approach. Another kind of taxonomy, what we looked at is classifying based on data sets. So a lot of previous papers, they have done like a lot of evaluation on the traditional data sets, which is the KDD data set, KDD99, which is like a very famous IoT data set, which is a very famous uh, a data set for intrusion detection, but it's not specific to IoT data. So in this paper, we have looked only at those papers which evaluate the model on IoT specific data. The reason is that because a model which might work very well on a traditional KDD data set might not work very well in a real-time environment, especially when it is looking at IoT specific labels. So this is one more classification we did based on IoT datasets. So bot IoT is one very famous dataset. IoT 23 is the latest dataset by Alani and Miri. So they have a lot of latest data. And then there are also like private data sets which are not available. So collecting all of these data sets is a huge pain point for security researchers. So one recommendation is that more people open source these data sets so that the research gets progressed better. Some interesting approaches what we saw just as a summary are like the supervised approach by KSL that combines like a decision tree classifier with SVM. Then an unsupervised approach by Lopez Martin, which proposed conditional variational autoencoders. The Rathore and Park one, which proposed a fuzzy C-mean. So that has like a really good accuracy and performs really well in production as well. Then we have like mix and match approaches, which are two-tier classifications. Then we also have approaches which use convolution neural networks. And then we also have approaches which use GANs, etc.
Mother's Day, can we do something from mom? Maybe I got something, but I don't know. Let's see what you got. Oh, you did? Yeah. Thank you, sweetie. Thank you. Yeah, but she hid it somewhere.
Also, the choice of using the right data set is very crucial. For example, UNSW has released a really good data set for IoT detection. These data sets which are relevant need to be more used rather than relying on the traditional NSL or KDD data sets. We'll look at a few of the pitfalls of intrusion detection using machine learning. So even though machine learning is really helpful in a lot of areas of security, it's not prone to pitfalls and the odd failure cases. So mainly we'll look at how we can classify a machine learning workflow for a lot of the papers we earlier looked at and see where would some of the issues occur and how we can avoid biases or try to mitigate them, or how we can try to mitigate the false classifications, etc. So the 4 steps what we can look at from Daniel Arp's paper are data cleaning and labeling. Then we have model design, performance metrics, and then finally deployment. So some of the issues which can exist at the cleaning and labeling stage are like sampling bias and label inaccuracy. So in sampling bias, like the distribution of data which is used to train the ML models is very different from what we use in real world data. So this happens when the variety of complexity of the real world data is not accounted for in those training data. So that might cause like a sampling bias. Then we have label inaccuracy. So supervised methods rely heavily on label information. So wrong or erroneous labeling might affect model performance. In the model design phase, we have spurious correlations. So sometimes our models are like prone to overfit or underfit the training data and not generalized to real world data. And also, if a learning model is adapting very well to spurious patterns instead of solving our actual task, then that would spoil our model accuracy in the real world. Then bias parameters. So when the learning parameters are not tuned using a validation set, so if you're just using a training set and a testing set, and tuning is not happening with a validation set, then we may not get a best performance during runtime. Then we also have like bias parameters and then inappropriate baseline. So we don't specify. The research in IoT with IDS don't have proper baseline or enough metric comparisons for all models to be evaluated holistically against each other, because there has not been a baseline set by anyone yet. There are not enough metrics basically to compare. For instance, if the labels are imbalanced, then accuracy is a poor metric, as it doesn't give an accurate measure for model performance on the minority class. Instead, for example, class-wise precision and recall could be a better parameter. So those kind of considerations, if not taken into account, might not accurately predict the performance. Then in the phase of deployment, we can a lot of models use a lab-only evaluation. So a lab-only evaluation might not accurately reflect uh, a real-time proof of success, because it's difficult to say that the performance is transferable to the real-world setting. So it's important to create like a lot of testbed environments so that we can evaluate them better. And then threat model, the security of the model itself. So a lot of issues might occur if we don't take the security of the model itself into consideration. Because new and new threats keep arising every single day. So the model itself has to be kept on retraining and updated regularly based on the current info of attacks in the IoT space. Also, the attackers can plant various toss attacks, evasion attacks, or they can try to retrain the model in a different way. Yes, especially if it is self-learning. So that's one possible pitfall we may need to avoid. So this table presents like a summary of all the papers and kind of biases which are present. And in some cases, we cannot successfully evaluate if those biases are present because of usage of private data sets or not enough information in the paper themselves. And also, like the purpose of this evaluation is not to downplay any contributions, because all of them are like really excellent papers, but we need to learn and understand the challenges in designing systems and also help researchers design more robust solutions in this space. We just want to discuss some of the biases which are present so that future research in this space is not prone to them. So we have leveraged Daniel App's do's and don'ts paper of Usenix and extrapolated that to the IoT space. Some observations what we see are sampling bias and label inaccuracies are found in many data sets. Evaluation of data sets themselves is a very tricky thing, because there are not a lot of data sets which are available. So security researchers are hand-tied in using them. More and more companies like Amazon Eco are trying to open source their data sets. So hopefully we can see progress in that step. Also, deep learning models, while though requiring less manual effort, they lack explainability, and also they are susceptible to learning wrong spurious patterns. So that's hard to identify. So that's one observation in most of the deep learning approaches. Then a lot of the papers fail in model evaluation strategy, discussing how do we realistically deploy this environment in a real scenario, whether be it a smart device or on an Echo Dot or any of these real world scenarios. How do we actually deploy? How do we evaluate what would be the time complexity of getting our response times, incident response systems activated, etc. So that is one evaluation strategy which is lacking. Then security vulnerabilities. Most papers don't talk about how to safeguard the models themselves from data manipulation or attacks, and how, especially if it's a self-learning model, how is the model being safeguarded from attackers trying to train it in the wrong way. So some of the challenges most researchers face in creating a robust system is outdated data sets. So as we discussed earlier as well, we don't have like a lot of data sets which are open source and which are classified based on the different type of attacks on IoT traffic. Therefore, if you want to build like a generic solution for a large scale production system, it becomes very hard to train, even though we get like a lot of good accuracy in our test bed, extrapolating that to a production environment becomes really hard. The second challenge, even to build such a data set, is collecting data points. Since IoT is a huge heterogeneous domain, collecting data points and feature sets is very challenging and a time-consuming affair. And also creating like a one size fits all data set is very challenging. So the suggestion is like to create different kind of data points for different kind of attacks, like spoofing versus DOS attacks, etc. Then another approach which is hindering our research in this area is a simulated environment. Building the simulated environment is itself a real complicated task and requires like a lot of constraints, cost, and maintenance. Another limitation is standardizing the performance metrics. So a lot of papers focus on either accuracy of statistics, false positive, true positive ROC, AUC score, but also we need to look at other model metrics of evaluation, for example, with respect to accuracy or the time taken to train the model, the response time, the computation complexity, the latency of response, the latency to trigger the incident response system or the autonomous agent in real time. So those kind of performance metrics, standard benchmarking is something which is a challenge to create. So some of the recommendations for improving IDS. So combining one approach which is looked at recently is to combine learning-based IDS approaches and try to implement a majority voting strategy and combine them with new upcoming areas like edge and fog computing for better results. Creating reliable IoT data sets. So because privacy is becoming a huge concern in collecting the data, so we can use techniques such as data masking and non-attribution so that we can avoid any privacy challenges in different areas. More research is also needed for better data cleaning and sampling techniques to reduce pitfalls and biases. We also need to combine like IDS and IRS for effective security. So we want to have like autonomous agents which will trigger an incident response system post detection by an intrusion detection system rather than having it manual. Also, we need to keep our models updated. They need to be continually updated for new threats which are getting detected every day. Also, another suggestion is like we have to collaborate more, we have to promote more collaboration between machine learning and security domains, especially with to minimize drawbacks related to model training, selection, testing, cross-validation, model security, sampling biases, etc. So another paper by Toralba from MIT, so that has really good guidelines on how we can avoid, try to mitigate biases in our data set selection, and also how we can create referential guidelines from an ML perspective to be used in other domains. Also, we need to look beyond standard accuracy measures, like F-score, ROC, AUC curve, etc., and create a generic model benchmark estimation method. So that comes to the end of the talk. So I'll just conclude with the urgency for IoT security. So with a lot of exponential growth in IoT users, we see that we need to have more and more robust IDS systems, which are production grade efficient, not just lab grade efficient, so that they can supplement our traditional computer security methods to maintain our confidentiality, integrity, and availability of our network perimeters. And this paper then explores the nature and architecture of IDS, all latest papers which use the latest IoT specific data sets, create a taxonomy, look at the biases and pitfalls in the machine learning pipeline for each of these papers. So the future outlook for this area is very interesting. It's rapidly evolving with new ML techniques being researched on every day, and also new IoT threats which are coming up every day. So it's a very increasing demand for security researchers in this space to build strong security systems which can be implemented not just a single industry wide, but across industries. And also there's a lot of scope for building standardized solutions which can be taken as the groundwork for future research. That's all from me. Any questions?